So, what if I told you we could teach a machine to master something really complex without writing a single line of code telling it how to do it? Sounds kind of like magic, right? Well, that's the whole idea behind reinforcement learning. Today, we're going to dive into how AI learns not from instructions, but from trial, error, and a really clever system of rewards. Let's get into it. Okay, so picture this. You've got a robot, and your job is to make it walk. But the physics, the balance, the coordination, it's so complex, there's no way you could code every single muscle movement by hand. You'd be there forever. So, what do? This is exactly the kind of problem reinforcement learning, or RL for short, was made for. See, it's not about giving the machine the answers. It's about just giving it a goal and then letting it figure out how to get there all on its own. So let's meet our little hero for today. We call it the agent. In this case, it's this little robot dog. And its first attempts are, well, they're not exactly graceful, are they? It's clumsy, it faceplants, it basically has no clue what it's doing. And you know what? It's a lot like watching a toddler learn to walk, right? Just pure, uncoordinated, fall down, get up again, trial and error. So the big question is, how does it get from that, the clumsy mess, to a confident walk? The answer is actually a really powerful idea that we all understand intuitively. It's basically a digital version of the good old carrot and stick. The core idea here is surprisingly simple. The agent tries something, any action, and the world around it gives it feedback. A good boy for a good move, which is a positive reward, or a nope, try again for a bad one, a negative reward. And just like that, its entire mission becomes a game. Get the highest score possible. The key is it's never told the rules. It has to discover them just by seeing what happens. Okay, so this is the fundamental learning loop. Think of it like this. First, you've got the agent. That's our robot dog. It's in an environment, the world it exists in. The agent takes an action, like, say, moving a leg forward. That action puts it into a new state. Maybe now it's a little off balance. And for doing that, it gets a reward. Could be a tiny +1 for moving forward or a -1 for wobbling. And this whole cycle, state, action, reward, just repeats over and over and over again, thousands of times. With every single loop, the agent gets a little bit smart. Let's make this a little more concrete. Imagine the agent is this car. Its only goal is to keep driving without overheating. Simple enough, right? It can do two things, drive slow or drive fast. Now, if the engine is cool and it drives slow, it stays cool and gets a nice little +1 reward. If it drives fast, the engine gets warm, but hey, it gets a better reward, +2. But, and this is the important part, if the engine is already warm and it decides to drive fast again, boom, it overheats. And that comes with a huge -10 penalty. So the agent has to learn, through experience, to balance chasing those juicy +2 rewards with avoiding that catastrophic -10. So what happens when you let that simple little loop just run? Not for a few minutes, but for thousands, even millions of cycles. Well, that's when things get really interesting. That's when the magic happens. Let's go check back in on our little robot dog and see how its schooling went. And here it is. Just look at that. On the left, that's where we started, the clumsy, falling over mess. And on the right, after thousands and thousands of trials, falling, getting back up, tweaking its movements, and learning from all those little reward signals, it's actually walking. And this is the incredible part. Nobody programmed it how to walk. Nobody told it, move this leg, then that leg. The robot literally discovered how to walk, all by itself, just by chasing that feeling of a positive reward. And that really brings us to the core takeaway here. The agent is never, ever given a rule book. All of its learning is based on what it actually experiences, on these observed samples of outcomes. It falls down, it gets that negative feedback, and its internal logic goes, okay, note to self. Don't do that again. Then it stumbles forward a tiny bit, gets a positive reward, and it thinks, ooh, that was good. Let's try more of whatever that was. Okay, so we get that it learns from experience. But how, exactly, does it use all those memories of good and bad moves? Well, it turns out there are two main schools of thought on this. Two different ways to turn all that trial and error into actual wisdom. Let's check out these two paths. Let's use a maze analogy to break this down. First, you have the model-based approach. This is like being a careful planner. You explore the maze a bit, and you use that information to build a complete map of the whole thing in your head. You try to understand how it all connects. Once you have that mental map, then you can plan the perfect path out. The other style is model-free. This is more like a just-do-it approach. You don't bother building a map, you just start running. You learn by rote memory, like, okay, turning left at that corner was good, but turning right there was a dead end. And there's a huge trade-off, right? The map builder, the model-based way, learns faster from fewer mistakes, but it takes a ton of brain power to build that map. The model-free way needs way more practice, but it's usually a lot simpler to get started. And this visual shows you the difference perfectly. On the left, you've got the model-free agent. It's learning online, which means it has to learn by doing. It has to actually touch the fire to figure out that fire is bad. Ouch! Painful, for sure, but definitely effective. Now on the right, you have the model-based agent. Because it has that internal map of the world, it can think ahead. It can run a little simulation in its head and predict the consequences of touching the fire, and learn to avoid it without ever getting burned. And you can see why this is so important, right? The model-based way can be a lot safer and faster in the real world, but only if its map of the world is actually accurate. Okay, this is all super cool in theory, but what's the point? Where does the stuff actually show up in the real world? Well, the truth is the applications are already all around us, and the list is growing like crazy. Reinforcement learning is really the secret sauce behind some of the most mind-blowing AI breakthroughs we've seen. You've heard of AlphaGo, right? The AI that beat the world's best player at the super complex game of Go? That was RL. It's what teaches robots how to do delicate tasks like grasping an egg without crushing it. And yeah, it's also working behind the scenes in things like self-driving cars and even helping make the voice assistants on our phones sound a little more human. And here's a perfect, really fun example you can see today, the AWS Deep Racer. It's this small, autonomous race car, and you train it using exactly what we've been talking about, reinforcement learning. The goal, the reward, is super simple. The faster you finish the lap without crashing, the more points you get. And so, through thousands and thousands of simulated races, the AI in the car figures it all out on its own. The perfect racing line, when to accelerate, when to brake. It literally teaches itself how to race. And that really brings us to the big final thought here. We started with a little robot just learning how to take a few clumsy steps, and we've seen how that same simple idea, learning from trial and error, guided by rewards, can scale up to mastering some of the most complex games and skills imaginable. So the question to leave you with is this. If a machine can learn to race a car from scratch, what's next? What problems could we solve if we can teach a machine to master almost any task just by giving it a goal? The possibilities are honestly pretty staggering to think about.